Okay, for today is called Proof with Induction. And this is not an easy day. It's not impossible, but it's definitely in the top 10% of challenging things. Things that will stretch your brain, which some of you could use because class is a little too easy for some of you. All right, so let's start with something like this: 25 squared. Now the answer is 625. Now I know you know that means 25 times 25, but there's a way that'll get you that answer without having to actually go through all that work, and it's not called a calculator. I'm saying in your head, you can do that in your head. Anybody see something you could have done with the numbers besides doing 25 times 25 all the way out in your head? I'm going to give you another one and just see if you can see how to do this one. 35 squared is 1225. Maybe after you see a few, you'll catch on to the pattern. Okay, one more. 45 squared. Well, by now, usually somebody's got it. Somebody got it? Yes? It only works for something that ends in 5. You are correct. Yes? It's a good guess, but it is not 1825. Yes? It is not 2425. It's 2025. You guys were taking shots at it. I appreciate the effort, but now adjust your model and go, oh, okay, that's not going to work. But what if I did this? Yes? Nope. Yes? Yup. First person who's got one right. Now, of course, you could have done that in a calculator. Please tell me you didn't use a calculator. Okay. So you got a theory. Does your theory work for all of them? Okay. Now you probably got it. So what do you think works?
Well, I just saw it all ends in 25.
Yeah, that should be pretty obvious. Yup.
The first one, like the beginning number is 6.
Okay.
The next beginning numbers are 12. You add 6 to that. You add 8 to the next one, and then 10 to the next one.
So this one was plus 6. This was plus 8. This was plus 10. Interesting. All right. So the problem with your way is that if I jump up to like 95 squared, you're going to have to do all the ones in between. See what I'm saying? Anybody got a different way? Ooh, new hand. I know what you're doing, and you're doing it right. Nice work. This was 2 times 3 made the 6. 3 times 4 made the 12. 4 times 5 made the 20. 5 times 6 made the 30. So if you're right, then I'm going to jump. I'm going to skip one. 1, 2, skip a few. 75 squared, what should that be? 5625. Now, if I go check with a calculator, or go 75 times 75 over here, I could make sure that it actually worked. Okay, 5 times 5 is 25. 5 times, I'm doing it this way, 5 times 7 is 35 plus the other 2 is 37. 0 to hold the place. 7 times 5 is 35. 7 times 7 is 49 plus the 3, 52. And 5, 1 to carry, 12, 3, 4, 5, 6, 56, 25. Yay. Now, did I prove that that's always going to work? No. This is a pattern. And I checked it. But checking it doesn't prove it. And that's the difference. Today is called proof by induction, not I think it works. Okay? So I think this works. In fact, let's just extend it to even a tougher question like 105 squared. If we're right, should I take the 1 and go 1 times 2 and say 225? No, that wouldn't make any sense. But if we're right, it could be 10 times 11. Do you guys have that one memorized? 110. So should this be 110, 25? Now this one, I'd rather have somebody use a calculator. You guys got one on your iPad, right? Would somebody just multiply out 105 times 105 and see what it is? Yep, double checked it. All right, a couple people have double checked it and it is right. So yay, it looks like it's working. Just because I checked it with two numbers that are slightly different, does that mean it's always going to work? No, that's not a proof. All right, so that's what we're talking about today is how do you prove something versus I think this works. All right, that's a big difference. Because a lot of people think we proved it. We did it with two different kinds of numbers and it worked. So it's proven. No, you didn't prove it. All right, so there are 3 steps to proving math induction proof. All right, so I want to go to this slide actually first and show you. These are the 3 steps. Now I do not need you to rewrite all these 3 steps, but get to that slide anyways. The first step is that you prove it for n equals 1 or first available n or some easy number. So you basically, the first thing you do in an induction proof is one of those where you stick in a number and see if it works. But does that prove it? No. Next step is that you assume that it'll be true if you change variables. Do you get if I change from an n to a k, that seems like whatever the statement was should still work if I just change letters? But we do have to say we are assuming that. We are assuming if we change variables that that's okay. All right. Now, why should we use k? For this type of a proof, k is just the standard variable that you use. Like, for example, if I say pi, you guys all know, 3.14. It's a little bit more obscure ones. If I say L and W, you kind of know those usually go with length and width. Okay, but they're not like firm, for sure it has to be, right? But for a mathematician, if you say k, for a mathematician, they're going to go, oh, you might be talking about one of those proof by inductions because k is the standard variable you use for that. Another one that's a standard variable is m. If you say m to a lot of kids, they'll be like, oh, do you mean the slope? And yeah, y equals mx plus b. You remember that one? Okay, so the point is that k is the variable of choice for doing induction. So all we do in this second step, it's really lame. You just change the n to a k, and you assume that that's okay. And we have to make that assumption. All right, and then the third step is that if it worked for any randomly chosen number, like a variable, and it works for the number after that in a sequential list of numbers, you know what I mean, like 2, 3, 4, 5, and if I picked that it works for 5 and it works for the number after 5, then no matter what I pick, it would work for everything. Does that make sense to you? If it works for any number and the number after that, then no matter what number I would have picked, every number would have worked. That's just a way to think about it. So I could have just said you have to prove it works for k plus 1. But I'm trying to explain why that makes any sense at all. It's just to be like, if I say k is the number I picked, and you say, well, I picked k plus 1, well, then you're one bigger than me. Okay? Do you remember that from these problems? U sub n equals u sub n minus 1. Does that ring a bell? It could come back on the ACT test. Because this wasn't just us torturing you in higher algebra. This was called recursion, which is something that they have on the ACT. Sometimes they use a. A sub n is equal to a sub n minus 1. And what that means is this term is equal to the term in front of it. Usually we do something like this, plus 5. And that means, hey, any term is the term in front of it, n minus 1 will be the number right in front of it, right? Plus 5 more. Remember doing that? So if I had a list that started with 6, then any term that I pick would be, compared to the one in front of it, it would be the one in front of it plus 5. So then this next one would be 11, and this next one would be 15. So if I pick any random one like that, then the one in front of it plus 5. And that's the same idea where this is n minus 1. That's saying a term and the term in front of it. It's the same idea for what we're doing now. What we're doing now is step 1, get to the purple page. Step 1 is where we prove that this works for any number that we pick. Okay, well, first of all, let's make sure you understand how this works. This is important because this is not intuitive. That's a list of numbers. Do we know how long the list is? No. That's a list of numbers that could be any number of numbers long. It starts with 1, for sure. 1's the first term. But then you just keep going by, well, in this case, just adding 1. And then how many terms do you have? You don't know. It's n terms. Okay, so if I have only 1 term, here's where the mistake is. People go, so you want me to say n equals 1, so I'm going to put a 1 here, here, and here, and then 1 plus 2 plus 3 plus 1 should equal all that. No, then you misunderstood it. If n equals 1, then there's only 1 term, and there isn't all of that, is there? There's just 1. If n equals 1, there's only 1 term, and it's 1. What if n equals 2? It's a list. Then you get to have 1 and 2. And 2 was the last one on the list. Did we have a 3 then? No, we did not. 2 was the last number in the list. Are you getting that this is a list of I don't know how many numbers? Next, do you get the number of numbers is n? So if I said 4, that's the easiest one for you to understand, because then you see it's, well, there's 4 numbers, and that is the last number on the list. 4 is. And it happens to be 1 plus 2 plus 3 plus 4. But could there be 5 numbers on the list? Yeah. If I put a 5 here, then do you get, I'd also have to put a 4 on the list? Okay. So n is how many numbers there are. Does it look like I have 5 numbers? No. So then you got to be smart about this. This is a list of numbers. All right. So let's try it for the simplest case, which is n equals 1. So I'm going to put in a 1 right there. Does it really add up all of those? No, there's only 1 number on the list, and it's 1. If I put in n equals 1, now I'm going to put in a 1 and a 1, and now I'm going to figure out the answer. 1 is equal to, why was there only 1 number? Because it said n is 1, so there's only 1 number on the list. Is that the same as 1 times 1 plus 1 all over 2? Think about that. Is that true? Yeah. So it worked. If there was only 1 number on the list, I checked 1. Now, do I have to check another number? No, but it'll make me feel a little better. I'm going to try 2 now. If I put a 2 here, do you get this is not all of those things? It's just a list of how many terms? 2. And so it would be 1 and 2. Not all of those. There's n is 2, there's 2 terms, 1 and 2. And then if n was 2, then I have a 2 here and a 2 here, and does it still work? Is 1 plus 2 really equal to 2 times 3 over 2? 2's cancel, 3 equals 3. Huh, it seems like it's working. Have I proved it's working? No. All I did is I checked a couple numbers and they worked. Now, in this proof by induction, you have to just check 1 number. And what's the easiest number to check? 1. So you check 1. You see if when you put in a 1, and you only have 1 term in your list. Remember, this is in the context of why are we doing this chapter? Because it's about sequences. And this is a list of numbers. If we use 1, there's only 1 number in the list. It makes it super easy. Okay, so we checked n equals 1 and it worked. I'll show you exactly how your proof should look. You would say, let n equal 1. And then I would say 1 is equal to, because all of that whole side is just 1 number, it's 1, is equal to 1 times 1 plus 1 over 2. And you have to show that it really worked. And this is 1 times 2 over 2, so that cancels, so 1 equals 1. There. I proved it works for a simple number. Just like when we did our little 25 squared thing a second ago. We just tried it and seems like it works. Next, the middle step is the one where we just make an assumption. Let n equal k. And it is as dumb as this. We're changing the variable from n to k. Now, why do we have to change the variable from n to k? Because as a standard for using induction, k is the standard variable. So we just want to use a k because that's kind of like changing. I'm going to make our slope be m. Did you know that some people use this y equals ax plus b? We use m. Calculator that you have on your desk or in your backpack uses a. Do you have to be able to change between the two? Yeah, but what's your standard variable for slope? Most people say m. The calculator says a. Which one's right? There isn't really something that's right. We just all agree in Minnesota. Most teachers teach it as y equals mx plus b. But we could all be teaching it as y equals ax plus b if we wanted to. All right, so the standard letter here is k, so we let n equal k. And if I were you, I'd be copying this down so you have an example of one good proof. Okay, because you have to be able to prove something on your next test. And it'll have 3 steps. Let n equals 1, or actually any number you want. You pick in any number and you stick it in and see if it works. Let n equal k. Well, let's just recopy the original, except put a k in. What is that proving? It's not proving, it's an assumption. And we assume that k and n can be interchanged. Sorry, not an n. Okay. Now, if k is just like any term, if k is any number you want, if k truly can be anything, now our job is to prove that it'll also work if we let n equal k plus 1. That's the third step in the proof. First step, n equals 1. Second step, n equals k. Third step, n equals k plus 1. Now this one is going to test your algebraic manipulation skills. If I let n equal k plus 1, first of all, people typically want to say, well, then wherever there was a k, I'm going to put a k plus 1. And that's not exactly right. And it's kind of dumb, but I think you'll understand this once I do it. This is a list. And if k plus 1 is going to be the last term in the list, then wouldn't I have 1 plus 2 plus 3 plus k, which would be the last term, plus k plus 1 would be the one after that, is equal to, and then, since this side was a list, the other side wasn't a list. The other side just said, that's the answer. It wasn't a list of the numbers. This was a list. Okay, so then the other side is going to replace the k's with k plus 1s. Wherever there was a k before, there's going to be a k plus 1. All right, so I know this is a little intense, but this third step, this is the only time all year we're going to be referring to a question as R3/R4. As in, this type of a question is such a hard R3 that we could call it an R4. So don't be all stressed if you can't figure out this last step, because some kids won't, and it's okay. Some of you will be able to pull off this algebra, and it'll be no big deal. But if you can't do the actual solving here, You're all right. You can still get an A in this class. All right, so this, why don't I just change them all to K plus ones? Why do I have the K still in here? Because wouldn't there be a K if the next term in the list was K plus one? Yeah, there'd be a K there, and then there would be a K plus one after it. Okay, so that side's a list, and then this side, I did replace my K's with K plus ones. Wherever there was a K, there's now a K plus one. Okay, so now I need to actually use algebra to prove this. Now, let me make sure that you get, this is something that, again, is kind of new for a lot of kids. They don't understand why I can't do this. I can't just multiply both sides by 2 to get the 2 off of here. But sure, we've always been able to like multiply by things if we wanted to, as long as you do it to both sides, we can do that. Why can't we do that? I'm going to sidestep for a minute. Don't write this all down, but let me show you this. If I had 6 plus n equals 8, have you ever been asked to prove that? No. The teacher just says, that's true. So it's actually, up until now, that's just been a true statement. And now you got to figure out what n has to be, assuming it's true. Now it's kind of weird, like, well, why wouldn't it be true? Well, we aren't going to assume that this is just green statement here. We can't just assume that's true. We got to prove it's true, and that's different. See, here, I can just subtract 6 from both sides, and n equals 2. Why can't you do that? Because in that, you're assuming that the original statement is true, and we can't assume that. If we can assume the original statement is true, then if I assume this green statement is true, then why am I trying to prove it's true? You can't use one of your assumptions as the proof. Think about it like this. You are arguing with a flat earther, okay? And they say, well, the earth is flat. I assume that, because they really believe the earth is flat. That's their assumption. That's how they start. Is, well, the earth is flat, and so, well, you'd be like, you can't assume that. You can't assume that the earth is flat, and therefore, whatever. You know what I mean? Because if you can't just assume something's true and then use that as your proof that it is true. Okay? So if I assume that you're always wrong, see? So obviously my assumption was correct because what you just said. So think about it. I know this gets kind of deep, but this, in the past, you could always assume that that was true. And then from there, you could add stuff to both sides. So that's why you can't just add stuff to both sides here, because you don't know that that green statement is for sure true. So this is going to be true throughout your whole math experience from here on out. Whenever anybody asks you to prove something, in calculus, it'll be the same thing. They won't let you do stuff to both sides and just like add 2 to both sides or divide by 2 on both sides, because that would be assuming the original statement was true. So what you can do is you can manipulate the left side or the right side until, if I can do normal legal math tricks, you might say, to change that to look exactly like that. If I can not break any rules and just manipulate one side, then if I can get it down so it looks identical on the left side and the right side, then I've proven that it's true. Yes? Wait. If I added something to this side... Oh, I get you what you're saying. So like, what are the math rules you can use? Can you add 2 plus 3? Yes. You can absolutely add 2 plus 3. Yes?
Aren't there, like, you don't know how many numbers there are between 3 and k?
You are correct. We don't know how many numbers there are between 3 and k. I'm going to put a ... in there because I think technically that'll be better. You are right, and when I've written the proofs before, I usually do that. So good catch.
So could you add, like, a 5 to the 17?
you're making an assumption. But you can't just make an assumption.
So, but we know that 1, 2, and 3 are there.
It's a good question. No, we don't know that 1, 2, and 3 are there.
So, like,
Okay. I get what you're saying. So I'm going to show you how to do it in a second, and I think it's very elegant. But what I'm trying to get across is why can't you just multiply both sides by 2? Because a lot of people want to do that, and honestly, to avoid this whole conversation, a lot of teachers just let kids do that. In fact, I taught last year, and there was one of the teachers that was like, "You can just do that. Go ahead." He was so sick of arguing with everybody about why you can't do that. He just said, "Go ahead. We'll just assume that that's okay." Okay. So yeah, they assumed that that was fine, and then we talked as a math department. And we're like, "That's not what's going to happen on your AP tests, etc. You can't prove something by manipulating both sides." And they tried to use the argument of, "Well, you can if you assume each step that you're doing." It got complicated and long, but in the end, we agreed that we were going to only manipulate one side or the other. That way, it's the same rules this year as what you'll see in IB, as what you'll see in AP, and that is you can only manipulate one side or the other when you're proving something. Okay, that's what makes proofs a pain in the butt. In case you don't remember that, do you remember in geometry, did you have to do some proofs? All right. And you probably didn't even have that many because they removed them because, frankly, kids suck at them, and you usually complain a lot about the proofs unit because there's all these rules, and it's frustrating. You got to justify why you could do it because of this corollary or whatever, and kids generally aren't that great at it. So, yay, it's my job to get you back into rules about proving things. Okay, so moral of the story, can I change? Some of you aren't paying attention anymore. Come back to me. Thank you. Can I manipulate both sides? No. I can only manipulate one side or the other. And from what I've seen, you're always going to want to take the left side and make it look like the right side. Okay. Now.
Wait, it was like k plus k. Would you do k plus 1, k plus 2?
Is this going to be hard enough to just do k plus 1? You can't ask me the k plus 2 question first.
I know, but is that
Did it? I'm not going there. All right.
Yes, it does.
So.
Because it's like,
We did make one assumption in this. We assumed that when we let n equal k, that this would still be true. That is one assumption we made. Do you remember that? Remember how in the wording back here, it said, assume that? Okay, so from that moment on, if that's been assumed, then we can say that is true. Like, it's kind of like you and a friend are arguing with something and you're like, okay, we'll assume that Jack is better than John at tennis. Then, therefore, well, you both have to agree then, okay, yeah, we'll assume that Jack is better than John. And so you both agree on that thing. Okay, so if I assumed this to be true, then watch how this works. Let's see if you can handle this. Some of you will be able to. I can pull that out and put in what I assumed it was, which is that. So then, this can be replaced with k times k plus 1 all over 2. But wait, there's still this part. Yeah, there is. Plus k plus 1 in parentheses. Now, you get it was an assumption. We assumed that this was true, so therefore we can use that fact. All right, so I swapped out 1 plus 2 plus 3 plus k, because that's where you were saying earlier, well, how can you assume there is a 1 and a 2 and a 3? Because we don't know how many terms there are. Good point. So that's why we swapped that out, and now we don't have that problem anymore. Now, does this actually equal that? That's the question. So there's some tempting moments where you're like, can't you just multiply everything by 2? No, you can't. That's the thing I was telling you before. This is the proof. You can only manipulate one of the two sides. You actually can do it where you start and only manipulate the right side, but it's not easier. It's harder. I'm only going to manipulate the left side until it looks like the right side. And at this moment, we start saying, okay, what is different about the right and the left side? Do you get they both have a divided by 2 on them? But this one isn't all divided by 2. How could I fix that? Common denominator, so how could I do that? Multiply by 2 over 2. Now they've got a common denominator, don't they? Why can you do that? Can't you just multiply anything you want by 2 over 2? Yeah, because you're multiplying by 1. And that's one of the rules of math, is that if you multiply by 1, you get the same thing as you had before. You're always allowed to just go multiply things by 1. So I just multiplied by 1 in a creative way by using 2 over 2. Now, you're going to be tempted to multiply this all out. And that works, but it's extremely slow. So instead, don't multiply it all the way out. I'm telling you, don't do it. It'll just make it harder. Because at this moment, you can pull one little maneuver and be pretty much done. Who can see a genius move that will get it to look a lot like the right side, all in one step? Somebody see it? You want to share it with us, or you want me to tell? Because I can. I think the kids that think they have found it are not wanting me to keep calling on them, so I will do it. I'm going to say one last thing to give you a little hint. I told you that I would say this one statement over and over again, and kids would keep forgetting that that was the way to solve the answer, to solve the problem. And I just asked a room of really smart kids, and nobody could raise their hand and say, Mr. Server, if you finish that sentence, come on, you can do it. If you can factor it, you should. You can factor it. And it's the answer to all the really hard questions. You remember me saying that? In this class, it pretty much is the answer to all the really hard questions. And this is, once again, if you can factor it, you should. Do you see a k plus 1 in both parts of the top? Wouldn't it be nice if it was factored out front like that? See what I mean? The k plus 1 can be factored out. So that's why it's my favorite saying, is after teaching this class long enough, I realized, dang, pretty much every time it gets really hard, the answer is, if you can factor it, you should. All right. So the k plus 1 gets factored out because there's one here and one here. And then what do I have left? But, Mr. Server, it's wrong. You have a k plus 2 on the top. But that's going to be easy to fix. Do you get how so far it almost looks identical to the right side? The only thing is I have a 2 and they have a 1 and a 1. Isn't it okay to break up a 2 into a 1 plus 1? So is this a legal step to say k plus 1 plus 1? Sure. It's legal to replace a 2 with something that's exactly equal to 2. And then, believe it or not, I'd have to mark this 5% off because it's not exactly identical. What does it need? A parentheses. I would allow you to take that last step as a double step, because can you put parentheses around things that are added? There's a property. Official property is called the associative property. You can associate these or you can associate those and you get the same exact answer. Here's the associative property in action. Do you get I can put these two together and put those two together and it's still the same? So if you're adding things, it's the associative property of addition that allows that to happen. You're not going to be asked to cite the name of the property that allows it. That would be even worse. Geometry actually does that sometimes, where you have to do something right and then say why it's legal to do that, which is the ultimate right way to do it. But okay. So is that identical to that? Let's double check. Yep. I proved it. See why I called that R3/R4? I've showed you how to do it, but yet it's still so hard that a lot of kids won't be able to pull it off. And therefore, it's beyond what I can actually really expect you to be able to do on a test to like, you should be able to do that to get an A in this class. Okay, but we could put it as an R4. Okay, so let's do one more together, like from scratch. Now this is just showing you like a different way you could get your numbers. And don't want to try to do the toothpick activity right now. Get to this one, the orange page. Now remember, the left side is a list. Is there for sure a 1 squared in the list? Yeah, because you have to have at least one term or this doesn't work. Is there for sure a 2 squared in the list? Nope. Depends how many terms you want. What do you think the easiest case is to check? 1. So if you only have one term, that one term would be 1 squared, which is 1, which is the first term, and that means we wouldn't have these terms. So if n equals 1, we only have one term, and it's 1. So I'm proving let n equals 1. So then 1 equals 1 times 1 plus 1, 2, times 1 plus 1 divided by 6. Whew! Is that really going to be 1? All I did is put a 1 everywhere on this side. 1 is equal to 1 times 2, and then this is times 3 divided by 6. Ooh, 1 is equal to 6 divided by 6. 1 is equal to 1. It worked. So I was able to do the order of operations in the right order. You get it? You're supposed to go from left to right if they're all tied, and multiplies and divides are tied. And so I went from left to right, and I ended up getting 6 over 6, and it was 1. Yay! My formula works. Now, if you really wanted to, you could put in n equals 2 and prove another number works, but we don't need to. We're never going to give you a false statement and ask you to prove it's true. Okay? I mean, that would be cruelty on the test, or on homework either. Okay, so that did work. It's true, and if you didn't get it to work, go back and figure out where you screwed up, because it'll work when you put in n equals any number, like 1 is a nice one. All right, now I got to do the second step. Who remembers it? Let n equal what? And that's an assumption. We are assuming that it'll be true if n equals k. So I just recopy the same exact thing I see. It's the simplest thing. Keep it identical to the original, except put a k in it. I know it's a pain in the butt to copy all that, but it's a pattern, so you'll probably catch on to the pattern. Plus plus k squared is equal to k plus 1, 2k plus 1, divided by 6. So now all it is, double checking myself, because if I made one letter wrong there, if I didn't replace n with k properly, this will all fall apart. Okay, good, yay. Easiest step in the world, just replacing an n with a k. So where is the hard part? We could expect you to do steps 1 and 2. That part is considered actually an R2 level question. That's pretty easy. You stuck a number in, made it work, then you stuck in a k. But the third part, this part, that only, I'm going to say in this room, I bet you 8 of you can do it right now. See if you're one of the 8. We'll make sure everybody's getting started right. It's really easy to think right now I'm supposed to replace that k squared with a k plus 1. I am not. K's still in the list. I'm adding a k plus 1 as my last term. On the right side, you do replace the k's with k plus 1s. Wherever you had a k, you put a k plus 1. I wish I could move everything over. I could try. Whoa. Mind blown. There's a white box in the way there. Stop it. I need to hold still, white box. So just a second here. I gotta freeze that white box in place. Lock. Lock in place. Come on. Then I should be able to grab all of this and move it over. There. There. Whew. There's the setup. Remember what's tricky about it? On the left side, you're just adding something to the list. So you keep this all here. Why do we really want to keep all of that there? Because at this moment, you're going to replace all of this with what we assumed it was equal to, which is all of that. True statement up here. If it is a true statement, then I can replace all of the left side with all of the right side. And now I end up with k plus 1, 2k plus 1, divided by 6, plus this part. And I'll never touch the right side. I'll only manipulate the left side until it looks like the right side. I'm going to finish it, and I'll let you decide if you were one of the 6 or 8 kids that would be able to do this right this second. I'm hoping I get that number up to a higher amount, but that was a prediction. How many of you knew you had to multiply that by 6 over 6? Okay, that's a good sign. Why? Because it needs a common denominator, so that this can get added to that. All right. Do you get that all divided by 6 that I did at the end could actually be, if I put this in parentheses, divided by 6 like that? Either way would be okay, but I want it to really look identical to this side. And now, is it identical to that side? Just right now? No, I got a 6 here that I got to deal with. I got to figure out why is there a 6 there and there isn't on the other side. Who thinks they know what I do next? You know, some of you guys are going to get patterned into this, so you're going to be like, I'm really stumped. I'll give Mr. Server's favorite answer. If you can factor it, you should, because that's the right answer. Again. you're really stumped on a really hard question, it's probably, if you can factor it, you should. Do you get that there's a k plus 1 in both this part and that part? They both have a k plus 1 in them. So that k plus 1 can be factored out to the front. Look at that. There's a k plus 1 in the front on the other side. Wouldn't that be good? Yes, it would. Okay, so I could finish this one, but then you really wouldn't have much time to start your homework. So I'd rather have you start your homework with me. You really want to see this finished? Okay, all right. K plus 1 comes out. Just in case we end up running out of time, I'm going to tell you this. Your homework is, there's actually 2 of these. You're going to do only one of them. You'll do the first one like this. You're doing one proof. That's your homework, just one proof. It's the first problem of your homework. So if you want to be done with this one and you want to actually start working on your homework now, because we are down to that less than 10 minutes left, I'd recommend, well, I'm not saying I'd recommend not listening to me. That's kind of dumb. But I'm going to say you don't have to keep going on this one if you wanted to start your homework, because the one in the homework is easier than this one. All right. Do you having a hard time seeing which problem it is? I'll show you. Just making sure. Right there. And it's that problem. Okay, that one. Not the other one. The other one's pretty brutal. This one. All right. There's a toothpick activity, which we're obviously not doing. All right, so I'm factoring out the... How much time do we have left? It's officially over now. I will try to finish it while you guys go, okay? Because you need to go to your class. If you want to watch a video for it, you can. All right, so I'm recording this, so I'll keep it going and finish this puppy. All right. I don't want to make you late to your next class so you can see the end of a really hard proof. Don't think it's worth it. Have a great day. I'll pause for a second while it gets loud here. Okay, some kids really wanted me to finish this, even though the class is over, so I said I would. And welcome back, those of you that were gutsy enough to want to see the ending of this. So, if I take this k plus 1 out of both, and I'm factoring that out. Why? Because it's here. So then I know that I want it in front. If I factor that out, what would I have left? I would have... I'm going to for the ease of my eyes, I'm going to say I factored it out of this and this, but I didn't get rid of both of the k plus 1s. I just don't have it k plus 1 squared anymore. So what would I have left? K times 2k plus 1. And then when the k plus 1 factors out of this, I have plus 6 times k plus 1. So that's this and this. K plus 1, it used to be squared here, remember? And I factored that out to the front. All right, next, this k plus 1 is good. It's never going to move. It's always good from now on. It's the rest of it that I got to fix. So I'm going to multiply this all the way out. And this is going to be k times the 2k, makes 2k squared. K times the 1 plus k, plus 6 times the k, 6k, plus 6. Now, this, remember, is fine. This k plus 1's good. And now I'm going to add together like terms. 2k squared plus 7k plus 6. And guess what? It factors. As you can see, the hardest questions often just come down to factoring. So this one will factor. And oftentimes you'd see I'd put the 2k in front just because I happen to have my 2k or k plus 2 in the second position. I'm going to put the k plus 2 here. And again, I know some of you are going to think, why didn't you put the 2k in front, Mr. Server? It's just because I can factor in any order I want to. And do you get that this multiplies back out to this? Double checking it. That'd be k squared plus 3k plus 4k makes the 7k plus 6. So yay, it factors. And I'm almost done. Does it look exactly like the right-hand side yet? Nope. I'm trying to make it prove that it looks like that blue thing there on the right-hand side. And my next step is I've got a k plus 1 here, which of course is the same as the k plus 2. And so I'm going to do that part next. This k plus 2 could be broken up into k plus 1 plus 1. That's the same exact thing as k plus 2. Okay? And then this is still 2k plus 3, but wait. This is where you really have to get creative. I'm going to look and see what I have. I have a 2 times k plus 1 here. So I would really like to have another k plus 1. So how can I do that? I had to change a 3 into a 2 plus 1. Is that legal? Of course, you can change a 3 into a 2 plus 1. Now, my 2k plus 2, when I factor just that part, it'll have the k plus 1 that I need. So final answer, k plus 1. This k plus 1 has to be in parentheses. I can always add parentheses because of the associative property of addition. And then this one, do you get that right there? It's another factoring. 2 comes out. I have k plus 1. And then this plus 1 just drops down. And I only factored the beginning part because that's all I needed. And now, the left side is equal to, it's exactly the same as the right side. And there we go. I told you, that's like an R4 level question. That's a tough question. But some kids wanted to see how it could be done. And that's how you could use the algebra to manipulate that thing out to be exactly the same. Double checking it here. Oh, and then I forgot to divide it by 6 that whole time. This divided by 6 here should have been divided by 6, divide by 6, divide by 6, divide by 6, and then this is divided by 6. I'm glad I checked myself. Some kid would have said, but Mr. Server, it wasn't exactly the same. It's true, it wasn't, until now. Okay, there we go. That's the proof, and that's all I have for the video for today.